Hello, we're talking about the method of partial fractions. This is part one, the introduction. And so what does this method do for us? Basically, it's a guaranteed method when you're dealing with quotient functions. And it sits on the fundamental theorem of algebra. What is fundamental theorem of algebra? If you have, so before explaining this method, I want to tell you the fundamental theorem of algebra says if you have a polynomial of degree n, p of x, then you can basically factor this polynomial into polynomials of degree 1 that is linear. So let's say a1 x plus b1 times a2 x plus b2. Some of these are of degree 1, some of these are degree higher. And then also some of the factors are going to be of degree, some of these factors are going to be quadratic. And the quadratic ones basically are going to be quadratics that don't have any real solutions. Those are the ones with complex solutions. So if you can, if basically for all the real solutions you will get a linear factor, and for all the complex solutions of p of x, this real polynomial p of x, you get a quadratic factor. And I'm going to just write it down, maybe a few. Let's say c1 x to the power 2 plus d1 x plus e1, and this is to power, let's say, k1, and it goes all the way to more and more of these quadratic ones. And so this is the fundamental theorem of the algebra that allows us to factor all the polynomials. The discussion is if you have a quotient function. Let's say the quotient function looks like this. There is, let's say, a of x over b of x, right? And there are two polynomials, so a quotient function. Like that, then you can actually write a quotient function if degree of a of x is bigger than degree of b of x, then you can always write this using the division, polynomial division. You can write it as d of x, which is a polynomial, plus r of x over b of x, and these two are polynomials as well. So the partial fraction method sits on these information. So you know, if you have a quotient function, you can always write it as based, and the degree of numerator is bigger than degree of denominator. You can write it as a polynomial plus another quotient function. This is the other quotient function, where the degree of r of x is less than degree of b of x, right? So these are the preliminaries that we need. We're going to use the purpose of these are when you're using it to do the partial fractions, then you remember these facts basically. So let's erase all that and do the next part. So let's say that we have a polynomial, a quotient function. What the plan is basically if the degree, here's the plan. One, consider the quotient function. Let's write it as a of x over b of x. Plan one is to write if degree of a of x is bigger than equal to degree of b of x, then find by polynomial division find d of x polynomial plus r of x over b of x, where degree of r of x is less than degree of b of x. So that's the first step. And why are we doing this? Because when the degree of the numerator is less than the degree of the denominator, then I can do the partial fraction, the method of partial fractions. And also, this way, if the polynomial doesn't match that degree condition, you find it as a sum of a quotient doesn't match the degree condition. You find that it can be a sum of a polynomial plus a quotient that is satisfying that degree requirement for the method of partial fractions. So that's it. That's the beginning. So assume from now on, assume that the polynomial you're working with is the degree of numerator is less than the degree of the denominator. And assume by the fundamental theorem of algebra, you have already broken down the denominator into linear and quadratic factors that are not, you cannot reduce those quadratic factors in real numbers. Basically, that means that there is no real root for those quadratic factors. So that said, and let's say that now, so you can express the new polynomial, or if the polynomial already satisfied the condition, into this format. You can write it as, let's say, k 1x to power, let's say, t plus k2x to power t minus 1 all the way to kt. And then the denominator is going to be of that format that we discussed, a1x1 x plus b1 to power n1 and a2x. All right, let's skip a few and say a mx plus bm to power nm, and also let's say c1x to the power 2 plus c2x plus, d1 plus d1. Basically, we want all the coefficients to kind of resemble each other. That's why I'm being obsessed about that a little bit. Plus e1 to power L1 and all the way to however many of these quadratic forms you have. So see, let's say LK, what do we have now used? Q. CQX2 plus DQX plus EQ to power LQ. So that's the one that I need. I want the numerator to be whatever polynomial it is, and then denominator to be factored. And I want the numerator to be of degree 1 less, at least 1 less than the denominator. Now, the funky part of this is that what we want to do in the next part is that we want to use the fact that we can integrate these functions. I can integrate 1 over, I'm sorry, yeah, let's say k over a1x plus b1 to power n dx. This is going to be a natural log, and I know how to integrate that one. I can also integrate, let's say, k over cx2 plus dx plus e to power m dx. When this is basically, there is no solution in the real numbers, when that's a quadratic with complex solutions. And so for that one, for this one, I would do a U substitution. For that one, I need to complete the squares and use a trig sub related to arctan of something, right? And so that's what I want to do, is to divide this complicated quotient function into these quotients, the ones that are integrands in here, so I can integrate easily. And that's the plan. And so now these are all the prerequisites that I talked about. And the next part is basically what I want to tell you is how to break this down into these type of fractions. And after that, we do some examples.